Okay, let's continue. So we have been looking at the common mode feedback, and in the last class we saw a couple of variants of them, and the basic idea is pretty simple. You sense the output common mode, and this is essentially a fancy way of saying that I'm taking the average of the two voltages, and you take this common mode and compare it with the reference voltage you want the common mode to be set to, and then we fix one of the current sources to be independent and tune the other current source based on that. And simplest way to get the average of two voltages is to use a resistive divider like this, and then use an op-amp and go and fix this. And the very first implementation of CMFB is where we didn't have to use an op-amp, and we can go and connect the sensed common mode to the Nmos bias voltage directly. So although this works, the one of the issues was the output common mode is getting set to VDD minus some VSG, which is not completely under your control. So to have a better control on this output common mode, we decided to use the op-amp here. And the moment you have an op-amp, with respect to the common mode signals, it looks like we have a two-stage op-amp put in feedback. So we have to make sure that things are stable and compensated, and that we did by putting this capacitor for Miller compensation. So this is the full circuit. And also we saw that if this parasitic capacitor creates an issue, which in practice it might, a simple fix might be to go and put a capacitor here to introduce a zero. This is something we saw in the Miller op-amp also, so that is this capacitor. And other considerations were this. So here we knew that we have to use an op-amp, but we saw that since this is a PMOS input, that is the output of this op-amp goes to the gate of a PMOS transistor, we saw using an Nmos input pair here is much better. And also, just like any two-stage op-amp, we have to make sure that the two drain voltages are nominally equal. For that, the source to gate voltage of these two PMOS transistors must be equal to the source to gate voltage of these PMOS transistors, which boils down to the fact that you use the same length and same current density for all these PMOS. And then we saw what happens in the differential mode. In the differential mode, things were fine, but the only issue was the things he used for sensing the common mode, that is actually loading your differential mode circuit. So the capacitors will impact the unity gain frequency, and the common mode sensing resistor directly affects your DC gain, right? So of course, to avoid this problem, you have to use a resistor that is much larger than the output resistance. But let us say this is a cascode to start with, the output impedance might be very large, so it might not be practical to use a resistor larger than your existing output resistance. So let's see what can we do to work around that. So let's see if I can, I'll copy this. So the idea is, oops, what did I do? Okay, fine. Yeah. So the problem we want to address now is the following. This is a very good CMFB, by the way. The only issue is that the resistors you put here is loading this node, and that is impacting your DC gain. So if I don't want to make sure that this resistor is loading this node, what can I do? I don't want this fellow to load this node. So should I connect this directly, or what should I do? You can put a buffer. So that's what we do typically. So let me just erase it and draw it. So as he suggested, you have to put a buffer. And how do you implement a buffer? How do you make a buffer? Common source follower, common drain. So I'll just draw two common drain structures like this. And I'll tap the output from these two, and then I'll do the averaging business as before. So this is what we do. So we put resistors here, and again this is the capacitor to add the zero, and this you go and connect it. This is one simple fix you can do. So now let us say I call these currents as some IY. So now if I call these voltages as VOM and VOP, that is the total voltage there. So this is connected to the gate of this transistor. It's biased with a constant current IY, which means what can you say about this node voltage? the gate voltage is VOM. VOM minus VSG or VGS. VGS at a current of, same will be the case with this voltage. So this will be VOP minus the same thing, VGS at a current IY. Which means what I'm actually averaging is not the actual voltages VOP, VOM. It is these two voltages. So what will be the averaged voltage here? I mean, VOP plus VOM by 2 is what we call as the output common mode, minus VGS at the current IY. Now, what do you think the negative feedback loop will do? The negative feedback loop will try to make which voltage to be equal to which voltage now? It will make which voltage to be equal to VCM ref? Right? So it will try to make this to be equal to VCM ref. But is that what you wanted? No. So what is one simple change you can do here so that VOCM is fixed to VCM ref and not VOCM minus VGS? I mean, here you want to add VGS, but I mean that means you have to put something here that is not possible, right? I mean, yeah, that's the simplest thing. Here, if I introduce minus VGS, that solves the problem, right? Either you add 1 to the RHS or subtract 1 in the LHS, both are same. So now that begs a question. I have VCM ref. How will I generate this voltage? I have a voltage VCM ref. I want to get VCM ref minus VGS at a current IY. What can I do? You should put another common drain. So I should not connect it directly. I should connect this also via another buffer like this. So here is where I connect VCM ref. Right? This is clear? So this is what you should do, and this is another way of making the common mode feedback. So I'll call this variant 3. Just a minor variation to what we saw in the last class. That's all. So now there is another common way in which this can be modified to avoid loading. So this is the existing CMFB that we have seen so far, right? We are trying to make changes to it to make it better. This is the crux of it. We are just making minor tweaks here to make it better. That's all. So one way to understand what can be done is the following. Let me call the small signal voltages here as VOP, VOM. So let's say right side I call this VOM, left side is VOP. So here the small signal voltage is VOM plus VOP by 2. So if I call the small signal voltage here is Vx, what can you say about the small signal current here? IA. GM times, let's say GM of some transistor, I don't worry about it for now, times, yeah, gate minus source. I mean, so now you see what's happening. The voltages here are first getting averaged, and the averaged voltage is getting converted to a current, right? So instead of first taking the average and converting it to a current, what can I do? It's a linear operation. I can convert to current and then average. And averaging in current means essentially I'm summing up two currents. Summing up currents is simple. I just put two wires. KCL will ensure that currents are added. Right? So that is something we can do. And which means that now I don't have to go and average the voltages now. Which means I don't necessarily have to use this fellow. Right? So let's say remove this completely. Right? Now my only goal is to make sure that I push in a current of IA which is equal to this in this branch. That's it. If I accomplish that, my job is done. Fine. So I'll erase this. So now I have to generate this current, and you can actually rewrite this in a different way so that it's easy to visualize. So I'll write it like this. I'll write it as GM by 2 times VOM minus Vx plus GM by 2 into VOP minus Vx. Both are same. Fine. So my job is now to first generate a current that is proportional to VOM minus Vx. how can I generate a current that is proportional to VOA minus Vx? I put a MOSFET. Where should I connect the gate to? And source? This is Vx, right? So that generates this portion. We'll come to how to get GM by 2. That we can change sizes, right? So how can I generate this current? I should use another MOSFET. Gate should be connected to EOP, source to Vx. Now let us say I have generated the currents. Now I have to add them. How will I add them? Yeah, I'm going to short it and put the rest of the responsibility on Kirchhoff, saying that the currents will get added. So now this current is fine. Now the only pending part is to ensure that the GM is GM by 2. Right? That is, compared to this transistor, if this has a transconductance of GM, you want each of these to have a transconductance GM by 2. So how do you think we can make this GM by 2? We have to change W. How much? Let us say this has a W width of W, right? How should be the widths of these two so that the GM is half compared to this? Root 2, 1 by 2, 1 by 4. Okay, what is GM in terms of current and width? Huh? Root 2 ID mu and Cox W by L, right? So what can you say about the DC current in the transistors compared to this one? Half. So the width current is going as 1/2. I want the GM to be half. What should I do to width? Huh? Oh, I mean, this is going as 1/2, right? I want this to go as 1/2. So what should I do to width? Fine. So this has to be width of. That's what you should. So this is another commonly used variant. I'll call it variant 4. But the basic idea is still the same. You sense the output common mode, use an op-amp and compare it, and go on and tune the current. And then now we can come up with whatever issues we find in this, we can do minor changes and tweaks to actually get this better. That's all. Cool. So now so far we have seen only techniques that actually fix the Nmos current and tweak the PMOS current. But we can do the other way also. It is not like I should always only tune the PMOS current. We can fix the PMOS current and tune the Nmos current also. So let's see how that can be done. So this is the diff amp. So let me erase all these things. So now the idea is I am going to fix the PMOS current to be equal to I0 by 2. So which means I have to generate a bias voltage here and feed it to the PMOS so that it carries a current of I0 by 2. How can I generate a bias voltage for this PMOS transistor so that the current is I0 by 2? Anything? I mean, is the question clear? Let's say I have a current source of I0 by 2. Let's say I give you a current source with the value I0 by 2. How will I generate a gate voltage for this PMOS transistor so that the current is I0 by 2? Yeah, so what do I do? I mean, can you, current mirror? Okay, fine. Let's say I don't know current mirror. What is current mirror? Tell me, what do I do? PMOS, but what can you say about the size of the PMOS? It should be equal to these two. Identical PMOS transistor I take and do this. The negative feedback will ensure that the voltage is correct. Okay. I mean, now, this is fine, but let us say now I don't want this biasing branch to carry the same current as this, right? Because it's unnecessary waste of current. So what can I do to reduce current here? Yeah, I can essentially say that this is 1/10 of this current. So what should I do to the width? Again, the idea is I want the same source to gate voltage. So which means current density has to be same. The lookup table parameter, I scale the current by some factor. Width also has to scale by the same. The same thing you would have done for fixing the Nmos current here also, right? I didn't show it there. Same thing you would do there also. Okay, so now that is done. So now we can actually do all the things that we have seen so far, sense the output common mode and tune the Nmos current. So all the 4 variants that we saw, you can actually do here also. So I'll call it N1 to 4. Tuning the Nmos current. All the 4 variants we saw, we can do it there. Now in addition to this, there is another common variant that is used. So let's look at that briefly. Oh. Okay. So the idea is this. So let us say now I fix the PMOS current value to be I0 by 2. Let us say now I also go and fix the bias voltage for the Nmos, but I'll make sure that the current in the Nmos is greater than I0. That is something we can ensure. And let's say I call this current to be I0 plus some 2 times IC, some extra current 2 times IC. I'll define it like this. So now if let us say finally the output common mode is properly defined. If the output common mode is properly set, what can you say about the currents in the Nmos transistor here? What will be the value of this current? No. Remember that if these voltages are properly defined, there is no change in the voltages. What can you say about this current and this current? They have to be equal, right? So finally you want this to be equal to I0 by 2. But as of now, if I look at it, the sum of these currents is I0, but this current is I0 plus 2 times IC. To satisfy KCL, what should I do here? I should provide an additional current source whose value should be. Now if I exactly know what is this current value and what is this current value, based on the additional difference I can put a fixed current source 2 times IC. But of course in practice you will not exactly know what is the difference, how much excess is this current. That's the issue, right? So now let me call this current as some IY. Okay. Now ideally you want IY to be 2 times IC, correct? But in practice, you cannot guarantee it because again, these are 3 independent current sources now, correct? This is fixed to say I0 by 2, but you have make sure that this is greater than I0. But how much greater than it is with compared to I0, that is something we do not know exactly. So we can't use a fixed current source. That much is clear. So now let us say I find that IY is say greater than 2 times IC. Let me erase this here. So this current is IY. Oops, sorry. I am saying let's say this is greater than 2 times IC. Then what can you say about the Nmos current? Is it equal to I0 by 2, less than I0 by 2, greater than I0 by 2? Why? Okay, so let's say if I write the KCL at that node, I have 2 times IN plus IY, I0 plus 2 times IC, right? So now what I am saying is my IY is greater than 2 times IC. So to keep the equation valid, IN has to be less than I0 by 2, right? Okay. So if IN is less than I0 by 2, what can you say about the output common mode? Yeah, I0 is greater, I0 by 2 is greater, so I am pushing in more current than the current that is getting pulled out. So which means my VOCM increases. As a corrective action, what should I do? Reduce? Yeah, that's the only thing to do. I need to reduce I. Is this clear? Remember that the current in the Nmos transistor is fixed by these two fellows now. Okay. I want the current IN to be equal to I0 by 2, which means I have to change IY so that it is equal to 2 times IC. And you will change the IY based on VOCM. So which means this can no longer be a constant fixed current source. What kind of current source it should be? Voltage controlled current source. And what will be the voltage controlling this current source? VOCM. Based on VOCM, I change IY. What is the simplest voltage controlled current source you know? Huh? Common source, simple MOSFET. So will I use Nmos here or PMOS here? PMOS connected to the supply. So that's the thing we can do. We can go and put a PMOS. I connect it to VOCM. So now you see, if I increase VOCM, what can you say about the current here? Decreases, and that's what you wanted. So we are fine. No need to flip polarities and all. Great. So now to generate VOCM, we can actually go and take the average of the two voltages using a resistor divider and feed it. But can we do something smarter based on what we have seen just now? Instead of using a resistor to average and then converting that average voltage to current. Huh? Yeah, because finally I don't worry about the voltages. I'm only dealing with currents. So instead of using resistors to average and converting that average voltage to a current, I can do what we saw here, right? So which means instead of having single transistor here, oops, sorry, I'll put two transistors. That's all. Okay. So now in steady state, finally if things are working, what is the value of IN? I0 by 2. Right. So if that is the case, what can you say about these two currents? What will that be equal to? IC, fine. Okay. 2 times IC should be the current provided by this composite branch, so IC in each branch. Great. So now tell me, what is the output common mode set to? VDD minus VSG of what? Yeah, this transistor is setting the common mode. The negative feedback loop is making sure that the gate voltage is defined to a potential to keep the current in this PMOS transistor to be equal to what value? IC. So VOCM is VDD minus VSG of the blue PMOS transistor at a current of, okay. Great. So again this works fine, but again one issue is again the output common mode is not completely under your control. It is getting set to VDD minus VSG. But there are situations where this can come quite handy. We'll see today at the end of the class. Because one nice thing is it is quite simple. You don't need additional op amps and stuff. So I'll call this variant 5. Okay, is this clear? Okay. Cool. To summarize the variants we have seen, the first variant we saw was this. We told we'll take the average of the voltages using a resistor and directly connect that to the bias voltage of the PMOS without the op amp. And then we decided to have a better control on the output common mode. We took the help of the op amp and connected that to the bias voltage. This was the second variant. And then we saw that the resistors here were loading the output node. So what was the fix we did? We used the buffer before the resistor. So I'll just draw it like this. I used the buffer before the resistor and the op amp was still there. And an alternative thing was this: instead of taking the average and converting it to a current, we did the common mode detection using MOS transistors in the current domain. So this was what we did, and again this was a part of an op amp. And the last thing we saw was having this excess current. So here if you look at it, the idea is slightly different. Instead of saying that I'll fix one of the current sources and tune the other current source, we'll say we'll fix both current sources, add an additional current source and tune that. Right? We add an additional current source and make sure this current source value we change to keep the currents in these two to be equal. Right? So that was the fifth variant, where we saw that additional current source was used. And I'll just say that it is like this. So now we have 5 different variants for common mode feedback. So as a designer, what is the thing that we should do? you are given 5 different options. So as a rational designer, what you might do? I mean, I have 5 options. Let us say you want to use it in your design. What would you do? How would you choose which is better for you? According to specifications, yes, but I mean, we should understand what is the nice thing with each of this, and what is the pros and cons for each, right? If you know that, then you can go and see based on your requirement what is better, right? So tell me now, based on what you know so far, what do you think might be a disadvantage with this, and what do you think might be a better thing with this? Loading, right? That was the reason why we moved to these 3. So here the issue was, I'll say, resistive loading. Whereas here there is no resistive loading, which is good because if you have a very high gain for your first stage, using this might not be a good option. So here there is no resistive loading, but remember that the gate capacitance will still be there. You will still have capacitive loading, but I mean, you can't have free lens, right? Something you have to pay. Cool. So now the downside with this is the following. So let us say look at one of them. Let's say look at this one. So here let us say these are the final outputs of your op-amp. Now you want the outputs of your op-amp to swing as high as possible, or you want the swing limits to be very small? You want the swing limits to be high. So let us say the positive output you want it to swing like this, negative to swing like this, as high as possible. Now these output voltages are directly fed to the gates of these transistors. Now remember that these transistors should remain in saturation. So which means these fellows will impose additional constraints on your output swings. You are no longer just limited by the transistors here with respect to the output swings. These fellows will also start and put additional constraints on what your maximum and minimum output can be. So if you want to have very wide output swings, this is not a great option. So that's the downside. I'll say here you have output swings is an issue, but here it is not a problem because it is connected to a resistor. Resistor is happy to take any voltage you feed in. So there is no issues with respect to the output swings. Now of course another important thing you might want to consider is this. See, finally when you design your final differential amplifier, you want the common mode gain to be small or large? As small as possible. So you can actually work out the common mode gain for each of these CMFBs, right? And then see what is the thing. I think I gave this as an exercise for you to work out. I'll give it as an assignment again. If you have time today, we'll look at the common mode gain for these 3. Again, all these 3 are very similar, right? Because fundamental is same. You use resistors and average it using an op-amp like this. So all these 3 will have similar common mode DC gain. This will have a different gain. So we'll see. If you have time, we'll see. Otherwise, I'll give it as an exercise also. So that is other thing. You look at the common mode gain and take a call which is better.